who's joined.
Yeah, hi, welcome everyone. Um, who's joining, and we're going to wait for another minute or two. We're seeing more people are joining, so we're gonna give another minute or two for all people to be ready before we are starting.
Hi, good morning. This is Arvind Kumar. James, I had sent you a note. Do you want me to send you slides because you'll be projecting?
Um, if you have, hey Alvin, good morning. Hey, if you have the slide ready on your computer, you can go ahead and present your computer.
Okay.
Since the timing is we have a lot of like speakers, and the timing is very 50 minutes, so we want to the speaker can we be able to control the on pace that way.
Okay.
Instead of me to click into for the speaker.
If you wish, I can just email them to you now, but I can also
But yeah,
project.
go ahead. Go ahead, email. We like to put the slide online as well after the workshop so that people can access it and download it or view it after the event as well. Just go ahead and share whatever the latest you have.
Okay.
Thank you.
Hey, James, it's Cliff. We're at 11:02, so I would recommend we get started.
Yes, we have quite a number of audience here now. We have about 50 people. Yes, good morning, everyone. Thank you for joining the Joint OCP JEDEC workshop for the standards for chiplet design with 3D IC packaging. As you all away from the invite and event, we doing this workshop so that we can for multiple purposes, like to be able to collect like feedback and from the industries on the standardization, see how we can help on that. So to begin with this workshop today, we have the agenda for 2 days, today and the next Fridays. So it's on the 14th and 21st. So it will be from 8 to 10:30-ish a.m. Pacific. So for today, we will have Cliff we do the high-level introductions on the OCP and what we are doing here, and then followed by Jawad will introduce more about uh, the Open Chiplet Economy or ODSA. And then before I will come back again to introduce you more details on this workshop and also the schedule and the program and also some of the rules. So, and with that, I will hand over to Cliff.
Thank you, James, and welcome everyone. I'm really pleased to be here just for a short kickoff on this workshop, which is a joint effort between JEDEC and OCP. And what we want to achieve is really understand how the OCP and the community can help move the market forward with potential standardizations around 3D chiplet, 3D design around chiplets. And this is part of our overarching vision for an open chiplet economy that we announced to the world about 18 months ago, where the OCP community, through its collaborations, want to bring forward standardizations tools and work on business workflows and engineering workflows to really support the ecosystem to allow a new silicon supply chain around having an open chiplet economy. And for those of you that are listening now, you should stay tuned. A very important point in our move towards a fully open chiplet economy is it going to occur on June 24th. So please take a look at our Open Compute Project Marketplace after the 24th, and you're going to see something new there with respect to the open chiplet economy. Also, I want to mention that we just launched a new work stream on high performance computing and AI, looking at modularity of chiplets and how can we put some standardizations there in place to move the market forward. That's being led by folks from Lawrence Berkeley Lab. And hopefully, if you're interested, please join that work stream. We can use people to help us move that forward. With that, I'm going to push it over to Jawad. Thank you, James, and wish everyone a great workshop.
Yes, hi everybody. Welcome to the ODSA Open Chiplet Economy workshop. So I just want to give you a high-level overview of what are we thinking in ODSA and Open Chiplet Economy. So as everybody now is feeling that AI is a big thrust and big commercial opportunity for everybody, our focus basically falls within the area of domain-specific silicon in the bigger scheme of data centers that OCP overall standardizes. So if we zoom into just the domain-specific applications, the chiplets that we are thinking about at the moment generally fall in the area of accelerators and memory, and then connectivity and die-to-die in particular. And if you've been following chiplets, you would notice that we have made a lot of contributions in terms of defining a bunch of wires. And then we have been standardizing some of the design aspects of chiplets. And this particular workshop is focused on one of our activities called Chiplet Design Exchange, which is the chiplet modeling foundation that basically ties the design in the EDA space as well as what the architects and the designers need. So we'll tell you a little bit about, what standards we have developed in terms of designing, a little bit towards the, you will see people who have been volunteers in Chiplet Design Exchange making presentation here. Next slide, James. So if you look at our overall activity in ODSA, you will generally see that our work streams fall in three categories. We do focus on open interfaces that are die-to-die and link layer, as well as we have a very exciting work coming out pretty soon, which is comparing different types of PHYs with each other for specific applications. You will hear a little bit about that today as well. Then we have Chiplet Design Exchange, which is the design tools. And we have two activities. One is the design kits and other are design flows. This particular conference is hosted by our Chiplet Design Exchange work stream. So you will hear quite a bit about it. Couple months ago, we had a similar workshop for our business work stream where we were talking about different economic opportunities that chiplets are creating. Please join us. The subscription information is available at groups.io and just search for OCP-ODSA there. James, all yours.
Thank you, Cliff and Jawad. So as Jawad mentioned, this is the CDS workstream, specifically focusing on the standardization. And recently we have published the joint effort between the JEDEC and OCP on the CDXML. We're also working on the material design kits and assembly design kits, which we will talk more in details later today. So with that, I'm going to the program for today. So as you can see the agenda, we right now presenting at the openings with the OCP, and then followed by our joint partners for the event and workshop with Michael will be presenting on the JEDEC standardization and collaboration with the OCP. And then after that, we have followed by the presentation by John Pot from Cadence, and followed by the another EDA company with Tony's, and followed by the many industrial like Alvin from IBM, and Java, and me will present again. And after that, we also have John Sharp from Lawrence, Berkeley, and then we have Huria from Tenstorrance, Narashim Ha from NVIDIA, Shah from InnoSim, and then we'll close the today workshop. And then for the next week, we have a similar programs and from different companies and organizations. With short time, I'm just going to show here, but we're going to highlight again in the next week. So as for the rules, before we begin, I think I saw you with 15 minutes presentation. We hope it will be 3 minutes, right? That will be remaining. We'll kind of remaining the remaining of the time, and then the audience can post your question on the Zoom chat. If we don't get times to answer them, we definitely will follow up posting after the events and post the the answer there. And also we will correct the slide from the presenter and post online as well. So here's a QR code for the next week, and please scan that. If you haven't signed register, please go ahead and register. So with that, I will hand over to Michael to be the next presenter from the JEDEC.
Hi, James. Thank you very much for that. Can you let me share my screen?
Yes, I'm going to start sharing right now. Go ahead. Thank you.
Okay. And please confirm that you're able to see my screen.
Yes. Thank you.
All right, so I'm going to talk to you about the component digital thread and the collaboration that we have between JEDEC and OCP around the chiplet design. So a bit about myself here. I leave that to you guys to read up yourselves in the interest of time. I'm just going to jump straight into the collaboration first of all, and then afterwards we'll talk about what it is that we have actually talked about. So first thing is back in September 2022, we started to have some liaison meetings with OCP and JEDEC, and we signed an MOU by both parties in December 2022. We then made a first press release to announce the new alliance between Open Compute Project Foundation and JEDEC, and that was published in January 24. I've inserted the link here for you on that. Now, our first task was the collaboration between the two parties to integrate the CDXML as part of the JEDEC JEP30 part model. So the JEDEC JEP30 part model was initially released in 2018, and it basically is an XML structure that represents how you can collect data about that part for the purpose of communicating it from one party to another party so that it can satisfy all of the data requirements as inputs to any software tool in the product lifecycle. Now, when we say any software tool, we mean it's not just competitive tools, but it is all the tools that participate in the logical design, the physical design, the simulation, the tests, the manufacturing, the supply chain. This JEDEC JEP30 part model is a standard XML structure for carrying that type of information. So we took a look at all of these CD XML content that OCP were working with. We mapped it into the JEP30. Anything that was missing in the JEP30 and inside the CD XML, we integrated into that. And then we balloted that in June of 23, and that was our first release of it. So we have a second press release to talk about that. We continued this collaboration between OCP and JEDEC in relation to die arrays. We got a sample of various die structures from different companies, and we looked at the way it was architected. The data itself was architected, and we expanded that architecture to make it more scalable. First of all, we tested out the existing architecture that was in the market, and we scaled it up to several millions of bumps. In fact, we went to as far as 1 billion bumps, and we found that the file size was up to 76 gigabytes. So we radically needed to come up with a new architecture for structuring the data for very large dies. And so we modeled it off the JEP30 part model, and we took the same data set and restructured it under the JEP30 into a new section called the die array, and we were able to get that down to less than 1 megabyte. So we released that in May 2024, and we issued a third press release on that. And we've been working now with OCP on new stuff going forward, which I talked about earlier. So the companies that were involved in participating at some level of the part model throughout its history has now grown to 52. But it's not just companies, it's also the different standards bodies. So we talked about, of course, the OCP here. We have signed an MOU as well with E-Class for the adoption of the part classification structure inside there. We've worked with the EDA industry, SI2, OEMs, GSA. So this part model has been gaining a lot of attraction across the industry. What's not written here is we've just signed an approved a project by IEC, it's an international standards body, for their review and subsequently and hopeful adoption of the JEP30. So the JEP30 standard is available on the JEDEC website. There's a dedicated page to that. This link up here gives you access to the latest version of the JEP30s. You'll see a description of what the JEP30 is and the participants and acknowledgements to the various standards bodies that helped us to evolve it to where it is today. And when you create a part model for an individual part, you can validate that part model through this link down here. So as you develop new XML files, you can always verify it against the actual schema. The structure of the part model is broken up into multiple different sections. There's a top section here, which is what we call the parent section, or really to do with the part identity. It comes from a specific manufacturer, and it has specific manufacturer part number identification. That could be a standards body with a standards ID, or it could be a company like Intel with a specific part number. And you can have one part number, or it could have a series of part numbers. And that then is connected to all the different technical content through the part details section. So we have manufacturing information, electrical information, environmental package, which also includes the die area, supply chain stuff, and thermal analysis. Now, to give you a scope and an idea of what is inside the part model, we took a look at the product creation stage, and at every step throughout the entire product lifecycle flow, we basically asked ourselves, what is it that we want to capture in the part model to satisfy a person working in this particular step of the product creation cycle? And as you can see, as you go down through this, in many cases, you see that the same set of data is being consumed by several different steps in the product creation cycle. So by capturing this data one time in electronic format, instead of having the users go to a data sheet, you enable the situation where software consuming tools can build interfaces to this JEP30 part model and consume this data in an automatic way. Just for the specific focus here of this meeting, I have put in 2 slides, one for electrical and one for package, that breaks down a very high level summary of the type of information that's contained in the part model. So starting off with classification stuff, you have electrical functionality and function mapping that goes from a simple components of discrete all the way up to very, very complex interfaces, where interfaces can be nested into each other to create things called a super interface. We have the ability to nest multiple different functions together inside a particular device, as you typically would have on a chiplet. And then we break out at the component level, at the terminal level, at various groups of terminals, be it differential pair, data buses, address buses, different types of interfaces. You can connect all of that to logical specifications and electrical specifications. And that set of specifications can be as simple as values on a resistor to as complex as various graph and trend data that you get on more complex type of devices. We have information around creating the schematic data for parts, where you can break up the component into fractures based on groups of terminals, based on functions within that the circuitry. You can have a thing called reference circuitry, which basically says that in order for this device to work, I need to connect it to the following components. And so I can take a definition of all that surrounding components that makes up this reference design and plug that into the part model. We also have added a section in there for software interface description through system RDL or IP exact. Now, at the more detailed level, when you go down to the terminal details, you have terminal properties, functions, grouping, differential pairs, terminal and function swapping. You have logical groupings, and then you can have also external circuitry requirement. You could say that for a 555 timer, for example, I need to connect a capacitor to this input in order for the 555 timer to be able to operate at a given pulse.
Then you have 1 minute remaining. Sorry to interrupt.
Okay. Then we have mapping arrays and to different types of physical structures, physical patterns that can be done. All of this then can be mapped to simulation files, functions, interfaces, super interfaces. On the package side, you have the different outline of the packages, the shapes, the location of all the bumps, the CTE, the Young's modulus, the assembly different technologies, you have keep in, keep out areas, and etc. And like that, right? Okay, next thing. All of this is triggered with digital signatures, which allows you to sign off each block of data that you present into the part model and gives you traceability of where that source of data has come from. And when you nest all of this together inside in an overall part model, you can still have all of that traceability there. So this last slide, the summary and the next steps for this collaboration team. Collaboration of OCP and JEDEC has been, in our view, very successful to date. We continue to get traction in the industry with other standards bodies becoming involved. JEDEC will continue to collaborate and support OCP. And we have two tasks going forward. One is the standardizing of the various design kits, such as the process assembly design kits, the material design kits, the test design kits, etc. But we're also supporting OCP with an upcoming chiplet demo in which there will be a group of different types of interfaces. I'm sure you're going to see this later on throughout the two-day presentation, in which you can have different bow interfaces, maybe UCIe, HBM interfaces. And we're going to, first of all, create individual library components for each of those interfaces as a separate part model. Then we're going to show how we can integrate all of these to make up a more complex IC and integrate it a second time when multiple dies and other functions goes on to an interposer. So that's the end of my presentation there. Thank you. If anybody has any questions, please let me know.
Yes, thank you, Michael. We probably have time for question, but people can ask question in the chat. We probably, if we have time, we come back at the end of the workshop. Thank you again, Michael, for from JEDEC for a great presentation. We're going to the next speaker here, John Park. Michael, if you can unshare your screen, and John Park, please go ahead and share your screen. So John Park from Cadence, yes, thank you.
All right.
We can see your screen.
You can see everything here.
Yes.
Thank you for the invitation to OCP for allowing Kate to give you our...
I'm sorry, John Park, can you do a full screen presentation mode?
Sorry about that. How's that?
Wonderful, thank you.
Okay. Thank you again for allowing us to give our opinion of what's happening in the industry around heterogeneous integration and chiplets and all those things. My name's John Park. I'm the product director at Cadence for the packaging tools. And the title of my talk today, my very short talk, is A Case for Standards as ICs transform into complex 3D systems. So I'll explain what that means in the next 5 or 6 slides. And I apologize for the fast pace, but we've just got very short speaking time here. So briefly, I think most people know what Cadence does, but just for those that are somewhat newer to this industry, Cadence provides the EDA design tools to design chiplets, to design the packages that the chiplets go on, and even design the boards that the packages eventually sit on. So we have a broad portfolio of tools for our digital IC design, analog and RF IC design, through all the verification, simulation capabilities, and all the multi-physics analysis that you need to sign off on that design. We're also doing quite a bit of work with AI, like everybody else. We have a platform that we use called JedAI that's kind of a repository, large language model for the storage of all the different design databases that are important, that you know, data is really the basis for AI. So this is a platform that allows the aggregation of those databases and storage and use it for reporting and those types of things. Cadence also has a lot of cloud-based solutions, and we also are an IP provider, quite a large IP provider. We provide silicon IP, chiplets, and die-to-die connectivity. And then last but not least, Cadence does a lot of work with the ecosystem, with the foundries and the OSATs and our customer base and standards bodies to try and make the overall experience of designing a lot easier for our mutual customers. So that's a little bit about Cadence. Let me switch gears and talk, kind of give you our view of really what's happening in the industry, which kind of sets the context for my next couple of slides here. So what we really see happening in the industry is the right-hand side of this picture. But if we look at the left-hand side, That's the traditional multi-die. I know multi-die to some people is kind of a newer term, but it's really not. It's we've been doing multi-die packaging for 40 plus years, called it multi-chip module, system and package. But the objective there was to reduce the size, weight, and power of the printed circuit board. So we took die out of the packaged components, mounted those bare die in the olden days on wire bond attach, eventually flip chip attach onto a laminate or ceramic substrate. And that will continue to happen. But that's kind of the history of the multi-die side of the story there. So there we've had tools in this space for over 30 years now. And again, that will continue. But what most people are talking about today is the right-hand side of this picture, and that is the disaggregation of big digital monolithic chips. Some of that has to do with size limitations. We can only build a chip up to 850 millimeters squared. The other things have to do with the more modularized form factor based strategies. When you build big chips, they don't yield, so they cost a lot more money. And then a lot of people are looking at this next generation of packaging to get around the memory wall by putting HBMs very close to a processing device inside of right next to it inside the package. So that's kind of what's happening, is this disaggregation of SoCs into these building blocks that we used to call dielets and now call chiplets, that are pieces of that SoC. And then we need since we're disaggregating this, we need an aggregation platform to bring all these chiplets back together, whether they're side by side or stacked. And that's where packaging comes in. So packaging is really kind of the center of the universe right now. We're sitting between simplifying and streamlining and reducing the power of a PCB. And we're also responsible for the aggregation of all these chiplets that are being blown apart. So, but the last piece of really what's enabling this are advancements in packaging. And most of this is coming from the foundries, but we see things like silicon interposers and embedded bridges, and now even bumpless stacks with hybrid bonds. So that the foundries have made it much more possible for us to create high performance multi-chiplet devices by reducing the overall geometries that we would use typically in a laminate-based package. We can do in a silicon process and increase the functional density. So that's really what's happening in a nutshell. And why I talk about that is really where I see a lot of the challenges going forward, but based on the customers we talk to. And that is this convergence of what we do in system design, so board design and multi-die packaging, with what we do on the digital IC side of things. We basically are seeing the convergence of the expertise needed to design one of these complex 3D IC systems. And we also see the complexity in the number of tools because of this. So for example, I'll give you one example. If you're a digital ASIC designer, I've been designing ASICs for the last 15, 20 years. Something like signal integrity was not on the forefront of your mind. You were concerned with flop-to-flop timing. Your device met your timing objectives. You were kind of good to go. Well, now when you go to multiple chiplets, you now need to concern yourself with the compliance of that communication interface, whether it's BOW or UCIe. You need to make sure that eye is high enough and wide enough that when you're simulating that channel between those devices. So that's an example of combining what we would use on the system side of the house, which is signal integrity tools, which we've had for 30 years, with what the die designer does. And so that's that overlap, and there's hundreds of these examples, but it really boils down to the overall complexity of designing one of these modern day heterogeneously integrated devices. And by the way, it doesn't get easier. It's going to get harder because now mechanical's coming into this in a bigger way. So, being able to model warpage, be able to model stress, be able to look at different cold plates or different heat sinks. Mechanical is starting to play a much bigger role, especially as we start stacking these things higher and higher together. So the design flows are going to get harder. They're already very hard based on the customers we talk to. And because of the broad scope of tools here, it's more common now for a company to have multiple tools from multiple EDA vendors creating potentially gaps in the flow. So that's going to lead to even more complexity in the design flows. So what that really all means is the packaging world is the wild, wild west. There are hundreds of ways of packaging devices. There's not like designing a digital chip where every couple of years I get a new node, few new rules, good to go. The world of packaging, we might get 4 or 5 new packaging technologies in a single year. They may not all work out. And then there are different types of packaging that are going to work best if you're going to send something up in a satellite versus you're going to send something in a low-end consumer product. So the other bit of complexity here beyond the design flows is just the fact that there are so many different ways for us to aggregate or package these chiplets together, depending on specific requirements. Everything from mechanical lead frame packaging up to the foundry-based packaging technologies that we have today. So again, this even further creates complexity in the design flows and really confuses a lot of the customers that are moving, companies that are moving to this type of processes. They don't even know where to get started, how to, whose responsibility, the design, was it the die designer, is it the package designer, who does this type of work that is kind of new to everybody in the industry. And so the next part of what I hear from customers after, the fact that the design flows are too complex, there's too many tools, requires too much expertise. The second most common thing I hear are I'm not getting enough information from my foundry, from my OSAT, for me to allow me to design my package. So we have, in the IC world, we have a PDK, process design kit. If I'm starting a new chip with a large foundry, they're going to give me a PDK, and that's going to give me everything I need as a die designer to be able to design do my layout, verify my layout, create the manufacturing output, and send them. And I have high confidence that the foundry can build that design. Doesn't happen like that at all in packaging. Packaging, it's some companies you might get a little design rule manual, so you get the AE's phone number, you can call and try and figure things out. But there's very little data to start up the design process. So we've started talking about assembly design kits. There's lots of names for it. There's PADKs, which I think is just too many letters. ADK is a little bit shorter, but the concept of an assembly design kit is similar to a PDK for IC design, and ADK would be for package design, and the A again is the key part. That's the assembly, and so John, really it's kind of the. Yep.
Sorry to interrupt. You have 1 minute remaining.
Okay. So it's the kind of the golden source of truth for the design. There are many different definitions for an ADK. I know PDKs, there's not a standard for that either, but they've become a de facto standard. It'd be better, I think, for ADKs there to be a standard around that. Some different ideas of what would be the contents of that ADKs. Cadence has been working with a few of our partners to start to release those. But there again is I think a case to create a standard and streamline the design process. So in summary, we're kind of in this world of multi-die, multi-chiplet design going forward. We're not going to go back to monolithic anytime soon. So this is we have to figure out these design flows and get around these challenges customers are facing from all the convergence of all these different technologies. And so I think that standards would help really bound the problem, the Wild West of packaging, to kind of put some boundaries around that and as a result, create some shorter design cycles. And that wraps up my overview. Thank you.
Thank you, John. It's a wonderful presentation, and from the EDA perspective, and I really appreciate. I think we're on time here. So with that, we're going to move forward to the next EDA company, Tony Mastroianni from Siemens. Tony is also a colleague at the CDX, work closely with me at the OCP. Let's welcome Tony. Please go ahead and share your screen and start.
All right, thank you, James. And I'd like to thank OCP and JEDEC for sponsoring this event. And what I'm going to talk today about is design enablement for 3D ICs. And we're going to be talking mostly about how what we call 3DKs support the design process. So really designing these 3D ICs is integrating chips. I like to define a chiplet as an IC that's been designed and optimized to be integrated into a package. And it really takes a system approach to do these designs. So you're covering all aspects from architectural planning and analysis. You're doing the functional design and test, physical design and planning, electrical reliability analysis, very complicated problem. So these are all the different aspects. What I'm going to focus on today, are you seeing my mouse?
Yes.
Yeah, okay, great. Yeah, I'm going to focus today on the ecosystem and design enablement and specifically with some of the standards that we're trying to drive through JEDEC and OCP. A little background here. I think James talked about the CDX group. So we are a working group. It's comprised of EDA vendors, designers, fabs, OSATs, material suppliers. And some of what we're really doing, our charter is to promote an ecosystem for chiplets workflows. And in developing these models, we had some kind of governing principles. We want to leverage existing standards that are applicable and no reason to reinvent the wheel. We'll develop new standards as required, machine readable models. This is important because you want to be able to use them in your design workflows and scripting, et cetera. And also neutrality from EDA vendors. So this will make life easier. 3D IC is a difficult enough problem. So if we can have a common set of standards and formats, that'll make it easier for our end customers. Just a few references here. You can look this up, but we started out defining a CDK, a chiplet design kit. There was a white paper. And what this talked about is models that are required for a chiplet. We also published our first JET part model back in 2023. Michael talked quite a bit about that. And then we recently published a pretty comprehensive white paper talking about design flows. And this is the link here. We'll be promoting that a little bit, but it's a very extensive report, which will go into a deeper dive on how all these flows work together. And then I'll talk about the 3D IC design kits. So 3D IC design enablement. So I think John talked about IC design enablement. These are your PDKs. These are all the things, well-established best practices that have been happening over the years. And what we're trying to do is have a similar methodology, but extend these concepts and standards to the packaging world, which has historically been a much more ad hoc process, if you will. So 3D IC designs require a different type of design enablement kit. And we call these 3DKs, 3D IC design kits. So I'll talk about what is in these kits. I'll define them briefly and then also explain how they're used in the design process. So these are basically a list of the different components. We have chiplet design kits, and what this is a recommended chiplet models to support the integration of a chiplet into a package. Then we have package assembly design kits. I know it doesn't roll off the tongue, but we did want to differentiate it, so it is focused to advanced packaging. Material design concepts. This is a novel concept where historically, when you're doing different types of analysis, the material information would be entered directly in the tool. Maybe you would get that information from material vendors, a very ad hoc process. So we're trying to standardize on a format that will allow us to define material properties that are required to support the analysis throughout the design process. And then we have package test design kits. And these are really similar to some standards in the 3D blocks where we're defining the test IO pins required to test the device doing wafer sort testing. So we'll start with the CDX. This is a pictorial diagram. We call it a chiplet design kit. And these are the models. So most of these, as you can see, are standard. We have thermal models, JEP and JEP 181 for plenty of IEEE standards in here for test. Behavioral models for simulation, power models, chip CPM models is a pseudo standard. Static timing analysis, .lib and IBIS and such. So these are all kind of existing, either standards or pseudo standards. Although the goal is to have, you know, machine readable models, there is still a need for documentation. So we're not saying that's not required. And security is an important concept. So what we're trying to do in the CDX is just define what security agents are included in the chiplet. So this is information, all the information required for the chiplet. And like I said, most of these standards existed, but there was a few gaps, and that's really what drove us to develop these CDMXL formats for the physical models and the electrical models, and they have since become extensions to the JEP 30 physical and electrical components. So in the physical models, we're looking at XYZ dimensions, tolerances, all the information that's required, not just for the design, but analysis and even manufacturing. Left def is a EDA view, which is suitable for EDA, but there's additional information and leveraging a lot of what was in the JEP 30 proper, which is initially targeted for PCB and system designs, but we're extending that to the chiplet world. Electrical things, think of it as an electronic data sheet. This would include operating condition, modes of operation, and it also includes an electrical definition of the interfaces, the die-to-die interface, as well as the external chip-to-chip interfaces. So the standard naming conventions for those pins are included. So when that IP is used in a chiplet, we can kind of reference, so you can map your pins to those models, and you can use that throughout your design flows and work scripts. And then the package test design kit, eventually this will probably be an extension of these JEP models. So this is a work in progress, and we have an active working group working on this. So we'll start with planning analysis. So really here, you're going to do some of your initial planning. We really, in building these systems, you're doing a decomposition of a system or a subsystem into different chiplets. So you need to define the I/O, the high-speed interfaces, the protocols, functional verification. So you need to simulate these. And then also you need to think about test, how you're going to test each of the chiplets as well as the overall chip. Using the kind of in the electrical JEP models, we do have the interface I/O in there, so that can actually be used to do interface-based design, where you can actually leverage some of these standards and be able to define your chiplet definitions, your physical models that include those electrical interfaces in there. And again, that can be very useful throughout the design process. So the CDK is used throughout most of the design flow. It's used for design planning, for test, as well as functional design and verification. So this is a bit of a noisy slide, but this is the package design kits. And really, the difference here is we have multiple vendors that really need to come together to come up with a cohesive set of rules in order to build, design, verify, analyze these different chiplets. So we'll take an example here where we have two chiplets. They're in two different fabs, Fab 1, Fab 2. So we need to look at the manufacturing rules of each of these fabs and come up with a common set of rules that will work, so we can have these chips plug and play. So this is going to drive the common chiplet assembly design rules. Okay, we also need to worry about the interposer technology. So there's going to be manufacturing rules there. So that also kind of defines the different connectivity, the pitches, the connectivity structures, TSV, and all that good stuff. And then we get to the substrate. We need to worry about the substrate, and there's some overlap there with the interposers, as well as the OSATs, because they're involved in doing the assembly and test, or maybe separate assembly and test companies. So all of these rules need to be looked at, all of these vendors. So by providing a format that we can describe this common set of rules, we can use that to drive the design process for your chiplet designs, your interposer designs, and even your substrate. So the substrates, we are coming up with a set of machine readable rules that can be used and reused for each of these different components. You also have constraints and guidelines, as well as your assembly stack, which will define how these things get put into the package physically. And then these will all drive the design, planning, and layout of the different components inside the package. And then these rules can then be mapped into the EDA specific tools to do the DRC, LBS, DFM type checks to do the physical verification of the chiplets. So reliability analysis. So this includes things like thermal analysis, thermal mechanical stress. So what we're doing here is introducing this material design properties. So this is a new open format for defining these material properties. So for electrical things, we have dielectric constants, surface roughness, and thermal conductivity, and thermal expansion, Young's modulus. So again, these are the material properties that are required to support this type of analysis for thermal and mechanical simulations. Similarly, on the electrical side, we have the rules necessary for that to support the analysis. So what first thing we need to do is do the parasitic extraction to facilitate signal integrity analysis, power integrity analysis, IR drop, electromigration analysis, as well as electromagnetic analysis and SIP level STA. So this is looking at chiplet timing for the lower speed interfaces in between those chiplets. So these, for the different components that need to have the extractions, we use these rules to develop the extraction decks and the PDKs. And then for the analysis, we're using the CDKs, so many of the views that are necessary to do the analysis, as well as the material properties, are used to create, to support the signal, all of these analyses that I just talked about. So the intent here is to put this information in a common non-EDA neutral format, machine readable, so that each of the respective design analysis tools, verification tools can use this information, and the EDA vendors would support these different formats for the analysis. Moving next to test, validation, and planning. The idea here is there is a test view, if you will. So in that physical and electrical model of the chiplet, we have the information that would be required to build the test hardware, to build a probe card, to do the wafer sort testing. We also have embedded analytics. These are IP that's put into the chiplets. So this is going to be required to be carefully thought up during the system level planning and integration, and even the physical design. You need to know where those get put. It also needs to be accessed through your DFT interfaces, and to support the 2.5 and 3D testing strategies.
So you have 1 minute remaining.
Okay, I'll need 1:30. This is the JEP 30 model. So I talked about the CDX model, which is kind of shown here. So strictly speaking, the new JEP models, the JEDEC models here, as well as the new PDDK, will form the basis of the part model. And then all these other views are additional models that are required for a chiplet. So in the part model, at a minimum, there will be a checklist that will define which models exist. And there's many different flavors and formats that can be used for power modeling and such. So these are suggestions. And then the JEP model also has the ability to actually put those models in there and deliver that. So the part model also serves another purpose. It is a JEDEC standard, and it can be used to facilitate a chiplet marketplace. And again, that's kind of in line with our charter. So chiplet suppliers can provide their information that can be used for potential users, and then the chiplet consumers or diners consumers would use that. So chiplet suppliers can use this JEP30 formats to provide information to the respective customers so they can suit a suitable reusable chiplet, which is the goal. And they can look at the functionality, different views that are available for the design. And then the actual designers can, search to see what's looking can actually be used to do a procurement. So you can look at different models and do trade-off analysis, look at the risk, and then actually potentially procure that IP directly from the IP vendor. And then they're used for the actual design. So these models are used throughout the entire design, planning, simulation, and manufacturing handoff process. And last but not least, this can streamline with the views that are necessary to support this design off into the manufacturing process. Okay, I thank you.
Thank you, Tommy, for the great presentation. So they were exciting updates from the OCP and JEDEC. We definitely are going to continue showing this progress in upcoming OCP Global Summits. And with that, we would like to move forward to the next presenter, who is Arvind Kumar from IBM. Please feel free to start and share your slides.
Okay, thank you.
Hey, Arvind, are you able to share your slide?
I believe so.
Okay.
And I apologize, I'm on the last page, so let me just start from the beginning.
Yes, we can see your screen. Thank you.
Wonderful. And let me go into a full screen mode. Okay, that should work.
Yes.
Okay, so the title of my talk is Dating and Marrying an AI Chiplets Perspective. So let me start with a little bit of a historical perspective. So IBM has developed an AIU SoC accelerator chip, which you may be familiar with. That's shown on a PCIe card on the left-hand picture. It's a monolithic SoC, about 300 millimeters square in area in a leading node technology. It has 32 AI cores. Actually, it has 34. 2 of them are spare, so it's 32 plus 2. And we are actively bringing this up and testing it on a lot of different AI models. The question is, what do we want to go to in the future? So we certainly see the benefits of chipletization. So our future vision is towards a set of chiplets on an SiP, as shown on the right-hand picture. And what does that mean? That means we want to essentially disaggregate the SoC that you see on the left into a lot of different components and do this in an optimal way. The main part of this is the AI cores. That's the compute engines. And that's what we would like to really focus all of our attention and energy to. On the other hand, there are other parts of this that includes CPU processing units, and it includes a lot of nest functionality that includes management units, the memory controllers, and the I/O. And those would be components we would like to see in a chiplet format that we can potentially reuse, which would enable us to spin out the AI core part of it, the part that we in IBM research have really focused on, with faster time to market and lower development costs. So I did fill out this table that we were requested to do. Our potential product is, again, this is from IBM Research, is an AIU accelerator in a chiplet format, and we are targeting specifically edge applications for this. And our target customer would be partners in the edge computing space that would benefit from an AI chiplet capability. So to be very clear about it, we as IBM cannot develop every chiplet that's needed for this kind of a package. So this would be more like the heterogeneous integration aspect that was shown in some of the previous talks. We're currently in the design phase. And I kind of group these business issues into 2 groups. One is kind of dating, and that's exploring compatibility of our AIU chiplet with other chiplets. And the second one is more committing, that's marrying and combining AIU chiplets with other chiplets to address targeted domain-specific applications. And you can see a little cartoon of the kind of architecture notionally that we have been thinking about. Again, this is a very conceptual picture, but it shows our AI chiplet, which is in blue, in combination with a number of other third-party chiplets. These could be direct connections, or they could be through some kind of a centralized hub chiplet, which then enables an easier connection to other third-party chiplets in the ecosystem. So dating. How do we explore the compatibility of AIU chiplets with other chiplets? The first thing is we really need an architecture simulator to guide towards an optimal chiplet configuration. So unfortunately, there doesn't really exist an eHarmony or a Match.com for chiplets that I'm aware of. You could try typing into ChatGPT, but I'm kind of doubtful you'll actually get something that's very productive or useful. So we are looking into how do we really model this from an architectural point of view. And part of this involves taking what's already available or will be available in the marketplace and then combining that with our chiplets. So again, having a very standardized way of doing this and importing models, which could teach us about performance and power area, would help us towards finding an optimal chiplet configuration for a particular application. What next? Well, suppose we identify a chiplet that we want to use, and we can see that we've designed our chiplet with a certain interface in mind. That's the physical interface, and we see that we found another chiplet that has a compatible PHY, but are we really interoperable? And that involves going up into the link layers and the protocol layers, and there's a lot of agreement that has to happen. That's what I would view as our second big challenge in this dating phase. And then, well, we decide to go ahead and tape our chiplet out, which is, an involved process that involves a high expense. So we want to really get things right. But even if we succeed at all of this and we tape out our AI chiplet, we have a big question. How do we test and validate this when maybe the other chiplets in the ecosystem aren't quite there yet? Is there a validation platform that we might be able to take advantage of that is specific to an application that would allow us to test and bring up our interface, but also really test functionally what we want to target, even if we don't have these chiplets that exist on the right-hand side. The next phase of this might be marrying. So now we actually have the chiplets, and we want to combine them with other chiplets to address targeted domain-specific applications. So at this phase, we also identify some major challenges, and I think this is only a subset of them. But the first one I would talk about is packaging sourcing. So we have succeeded then in taping out our chiplet and potentially procuring other chiplets from the ecosystem to achieve the targeted application that we want. And we have at least been able to do some initial validation before, if there's some kind of a platform to do so. But we'd like to then assemble these, and we want to decouple the packaging from the chiplets because these chiplets could all originate from different sources or different foundries. We don't want to tie ourselves to a one-stop shop. We'd like to be able to do this independently. But because this is a domain-specific application, the low volume that we would probably anticipate could limit our choices. And having a facilitated, standardized way of doing this packaging and pushing it through, that would be one aspect that would be very beneficial to us. And of course, I think the second one is one that has been talked about. It was discussed in the last couple of talks as well, is the test and validation methodology. I think it's well known that this is one of the issues with chiplets, to make sure that we have known good dies, and then to package these and have tests along each step of the way to make sure that our final package has a high probability of yielding. Okay, so with that, I wrote up a little summary. Our potential product, again, is an AIU accelerator in a chiplet format, targeting an edge application. We are interested in partnering with others in this space that could benefit from an AI chiplet capability. We are in the design phase at present. We did identify as business issues, how do we explore compatibility of the AIU chiplet with other chiplets, and then how do we combine our AIU chiplet with other chiplets And some of the issues there include the test and the packaging. And I will add also, because of the last two talks, we do view EDA as also being one of the potential challenges, recognizing that there has been a lot of work from the main EDA vendors in the space. And then in terms of possible solutions, the development of domain-specific platforms, which would enable us to validate the chiplet interfaces and the compatibility, as well as the functionality towards the targeted application. The facilitation of packaging through something like an MPW-like framework for advanced packaging technologies with an associated prototype assembly flow, and the development of standardized test and validation methodologies. I think that was my last slide.
Yeah, thank you, Alvin. Like from the industrial perspective from IBM, I think like addressing some of the challenges and how they are tackling these challenges. And is great. We learn a lot of new perspective here. So I think like that's why we here in OCP and JEDEC, right? And together with others, industrial companies work together and trying to addressing these issues from the standardization perspectives. So we do have weekly meeting, as like Tony mentions. We're going to share in a bit also in the next presentations that we really welcome everyone to join. And we're also collecting the feedback and also like the challenges that we learned today. And we're going to hopefully addressing them, right, or follow up on these challenges in at the OCP. We're going to also like talk to Java, planning to have a session, during the regular weekly OCP open chiplet economy meetings, and talk about what we learned here, and also feel welcome everyone to join. We'll send out information and follow up as well. Thanks again. Alvin's especially I help to buy us some sometimes here. So with that, we can actually and go and move forward. With the next presenter, who is Jawad, right? Please go ahead when you're ready. And for Jawad, then I will also continue to talk a bit more about the works, ongoing works that Tony has mentioned earlier on the OCP in the 2D IC design development. Thanks again, Alvin.
Thank you.
Alvin can unshare your screen, and Jawad can go ahead and share it. Thank you.
James, let me know if you can see my slides.
Yes.
Okay. So I got half a slot because I think, so I have I believe 7 minutes, 7 or 8 minutes. But I will basically cover the utility of the work that we are doing in CDX work group. So I have two hats. One of them is the co-lead of ODSA project. And previously I was actually co-lead of CDX, so I happen to know quite a bit about it. And I want to show you something which we've created an alliance, a commercial alliance as Palo Alto Electron, which is the company that I represent here. And I want to show you how we are making use of some of the standards that we've developed at OCP. So if you look at our CDX work stream and the output that we have produced, we are focused quite a bit on the full life cycle of the chiplet value chain, including architecture, the design, fabrication, testing, and productization. So you will hear quite a bit about CDXML, which is a standard developed originally to model the chiplets. but it had life of its own. And then JEDEC joined us, and we basically are now taking it to the next step. So for the design side, we do have CDXML to define chiplets, and then now we are building reference workflows on it. And the next thing that's a big one is CDX-based design kits. So the important thing here is, these design kits are critical, and we are kind of like developing those for the benefit of industry. And then we're thinking about testing, and JEP30 is a great electronic data sheet for product development. So I'm going to switch my hat to the commercial side, which is, so as Palo Alto Electron, we did put together a small ecosystem of companies, which is growing at the moment. We have about 7 of us, and we basically collaborate with each other in our area of expertise and take care of various aspects. So Palo Alto Electron, my company, basically works on product definition and package architecture. And then we have design and IP companies, Anamoy Software, who you will hear from tomorrow in the next session. And then Trace Systems and Epirus, which is, I'll actually talk about them a little bit. On fab side, we have Hyperion, Promax, and ITES. So among all of us, we have basically the essential components for the manufacturing and the design side of things. We're still trying to increase our membership on the design and IP side of things. So in this short presentation, I'm just gonna show you a few things where we have made use of the CDXML based thing. So if you go to our webpage, what you will see is there is a simple browse, design, and manufacture. And if you click on browse, you will find a catalog. And this catalog is work in progress. And we basically are building, bringing in newer components into the catalog. And the first one that I'll mention, which I think there's quite a bit of interest, is, for example, high bandwidth memory version 3, right? And the talks that you have heard so far related to design kits, if you look at the way this is being shown here, so high bandwidth memory 3 on the right-hand side of it, you will see that there are some green tick marks and there are red tick marks, which basically would tell you what kind of models are available for these components. So you will notice that for this particular component, you can actually download CDXML, JEP30 models, ECXML models for cooling, and the power model, which is IEEE 2416. So all of this is built on the foundation that CDX has put in the open, and we are bringing in more particular ecosystem. Now, behind the scene, all of this connects into our design and the manufacturing that we have through the alliance. So I mentioned Epirus Sync, and I think some of them are here on this call. It's a very interesting chiplet that Epirus is developing, which is a high power voltage regulator, for example. With all the demand of power in data center AI, there's a need for this extreme power delivery, and they are one of the early companies working on one of those chiplets, and they are one of the partners in our alliance supplying these high powered voltage regulators. So what you will see in here, for example, in this particular catalog, you will see 2 sections. You will see a section which is standard chiplets, and that is the section that is generally available to everyone to browse. And these are basically dies, dielets, die size chip scale packages, which are available and needed for applications that are more on the automotive side or edge side of things. So you will see microcontrollers, sideband IOs. You will find some HBM and DDR and some FPGAs, some sensors, etc. These things are readily available, and some of these components actually get used in the bigger sized packages. The new and more interesting area is the custom chiplets and IP. And part of that is only available to the partners at the moment. But down the line, as we get permission, more and more of these components will be made available for general browsing. But they overall fit in the category of accelerators, die-to-die and die-to-memory bridges, voltage regulators, the high power voltage regulator that I gave you a sneak peek on, for example, optical transceivers, some custom versions of high bandwidth memory, SRAMs, network on chip. And this actually is in line with what Arvind was mentioning. So we'd love some dating and marrying of the chiplets here through our platform. So our platform, you can think of it as match.com for the chiplets. So Arvind, I'm going to talk to you offline to see how we can work on this together. And with that, I think I'm at the end of my 7 minutes to just say the one last thing, that if you are supplying IP or if you are developing chiplets or thinking about it, please talk to us. We'd like to expand our member companies in the alliance who are in that particular area. And you can reach out to me directly, or you can go to info@chiplet.us. So James, all yours.
Yes, thank you, Jawad. Again for another great presentations. And from the Chiplet.us and Power to Electrons, have been involved in Java quite a bit as well. This has been great to see a lot of these alliance working together, and also with OCP together working on this kind of standardization and using the some standard that we're working on, like the CDXML and JEDEC in this kind of catalog. At the OCP, we're also working on the some demo examples. I think using this kind of standard, I believe Tony David will probably mention in his presentation in next week. So and with that, let me quickly share my screen again. And a few things I would like to talk more, continue from earlier morning that I have mentioned about the works that we have been doing here in the OCP. CDXML, like you have been hearing multiple times, like earlier today with Tony's and with Jawad. So it's one standard, like, and also with Michael, that we have been released, and that to both OCP and also JEDEC. This is kind of like high level view. I think I vision that we have, like this slide from Tony, I think he has shared before. So we're trying to put all these different standards together so that we can, using this standard format throughout various design phases. So Tony has done a throughout, I think, in his presentation, how these different phases could benefit from this kind of standardization and also the standard format. And with that, I just want to dive in a bit more in details about the ongoing works that we have been doing. The checklist on top, which is a CDXML chapter, has been completed. We are working right now with the package assembly design kits, which Tony has mentioned. which we are in progress. We are targeting for the OCP Global Summit, which coming in October, and as well as a package material design case, which we are also targeting for the same times in the OCP Global Summit. In parallel, we also have the package test design case, which Tony has mentioned, which we have started recently. And then there's other standard that we have looked into in before, like the SoC IP libraries, the process design case, and also package IP design case, like which we will continue to involve after we completing like what we have been doing. So we kind of working on the like stages kind of proof, kind of like focusing on like probably I think like more immediate right now to the assembly, material, and test, and then before we move on to the next stages. So this is kind of like high level, I think like the CDA case, which is many of these things have power under the CDXML, and then they especially on the physical, electrical, and behavior side. And many of these, like most of you are familiar. I think like we all these kind of like part of the process. I think like throughout the 3D IC design, you need this one way or another, like whether you are designers, you are testing, you are manufacturing or assembly, you will require, I think, like some of the standard here and there, so that we can share the information and reuse the data, design data from one party to another party, or from one tools to another tools. That's kind of like the overall like what we are targeting for. So let's coming back to the right packaging assembly design kit. So right this is talking about all these assembly rules, all the stacking rules. So right there are parameters that we're aware of, right? Like 2D blocks, right? So just kind of highlight here, like something that right is important to the industry, right? That's why we're also working here, I think, like to addressing the issue. I think our focus is more kind of like broader and general sense. So this is kind of like one the structure that we're adapting, I think, like from Intel, like which is like we high level wise, like we do have like these like the header, like the layers, geometry, packs, and visual outlines. So like Intel also will be presenting, like they probably definitely going to talk more details about this. So we've been working with them in parallel, like to come up with the assembly design kits that will work for the industries. And next would be like the material design kits, which is like defining all this kind of material property, especially like in the like different dielectrics, like for different kind of like surface roughness, and in the electrical properties, I think which is important, like as these different materials like that you're using for different dielectrics, like will impacting on the design and also in the testing, as well as like the actual functionality of your products, and as well as like on the thermomechanical dynamic wise, like the materials are impacting on the thermal conductivities, like an expansion. So we use like the ML, I think, which is one of the like libraries for more policy of the material design library, but we will be focusing on the structure that is really applicable on the semiconductor side. So here kind of example here on the data typically sees like for the material data, I think which we cover, we're working on the XML schema that will.
James, you have 1 minute.
Yes, thank you for reminding. I usually do that, but I think it's nicer somebody to help me on that. So yeah, so this kind of like high level on this material information. So and next, I just want to summarize. Here, like we do have a bi-weekly meetings on every Thursday at 11 a.m. So we have all information on our Google Drive. But more important is like this is the link. Sorry, this is the link. That way you will be like subscribing, or you can also go into like OCP like calendar. So to look for the events and subscribe from there. So with that, I will end my presentation here and then move forward to the next presenter, who is John Sharp from the Lawrence Berkeley Lab. John, when you're ready, please feel free to go ahead and share them. Let me unshare mine.
All right. Can you hear me?
Yes.
Okay, so let's share. Let me see here. Okay, and then we'll present. All right. So I am from Berkeley National Lab. I'm department head for computer science, and we're a research organization. So this is more from the standpoint of computer architecture and some future needs. All right. So what's happening with HPC right now is that over the past 30 years, the measured performance improvement of HPC systems has improved by about 1,000x every 10 or 11 years. And it's worked like this like clockwork for decades now. However, if you look at the past 7 or 10 years, it's been fading very quickly. And now we're down to less than 3x every 11 years. And so business as usual alone is not going to deliver for that community. So specialization, this is nature's way of extracting more performance from this resource-limited environment. You know, we used to have powerful Raptors, Xeons, and power general purpose processors. After the end of Dennard scaling, this gave way to lots of many core. Here you see depicted a bunch of aggressive sparrows, and that's kind of what Intel's Knights Landing, the Cavium Marvell, and to a certain extent GPUs. Lots of lighter weight cores pursuing the food sources. But once you get to the post-Moore scarcity, as things slow down, as the improvements slow down, the critters go after different food sources. They evolve more specialized beaks, and this is the direction that the hyperscalers, Apple, Google, Amazon, and Microsoft are going. And so, you know, for us, we want to see, we see this as also the path forward for both science and AI in order to extract more energy efficiency in future generations of systems. I think we've seen plenty of examples of using chiplets to create specializations that accelerate the development of AI systems. This is also taking a page from the same playbook. How can we use chiplets to insert specializations for very high value parts of the scientific workload for HPC? So, you know, we believe in this move towards an open chiplets ecosystem where we can take a platform. The platform cost is the primary cost, and what we want is to be able to insert specialization into a platform without having to respin the entire chip. And the chiplets offer us a way to mix things like ARM IP, which is a platform that has compilers and firmware, with targeted specialized chiplets that can also optimize designs for our workloads. And a similar thing I think we saw earlier from IBM being able to do that for AI applications. And there's been a lot of great work, both on the die-to-die interconnect standard, test standards, chiplet descriptions, but there's a bunch of other guardrails that we need. I think we've focused, I think there was an awareness at the NAPMP meeting at Moffett Field a few weeks back that we've spent a whole bunch of effort on this first step here, the die-to-die, you know, UCIe and BOE, but that's not where it's at. We have all of these other aspects of the standards that need to be settled and agreed upon before we really truly have interoperable chiplets. So that's, you know, size guardrails, power delivery, thermal, wiring density, bump and assembly pitch guardrails. These have not gotten the focus that they've needed in order to promote this vision for the future. Batby Vinicota and I did together with some others in the community, Anu, did a thought experiment for what if we created size and power guardrails, for example, for HPC system chip, and what would that enable in terms of modularity for HPC? So this Fugaku thought experiment, we adopted the Fugaku chip because all of the details of the architecture, the layout and the areas and the speeds and feeds are documented very well publicly. So we decided to chipletize the Fugaku to perform this thought experiment with the idea that what would it look like if we put it in chiplet form, but didn't sacrifice anything in terms of performance. So full performance system, but done in chiplet form. And so once you do chipletize a Fugaku, you have on the left-hand side here the standard Fugaku and how it breaks down the subsystems into these chiplets. But if you work your way to the right here, it also opens up a lot of opportunity for modularity, reconfiguring the memory subsystem for more capacity, or reconfigure for an inference engine co-integrated with these things. Lots of different variants can be had at a much lower cost and a lot of reusability of the chiplets that are the modular components that build this up. So just that small thought experiment with power delivery, size, and air and what the modules would be opens up numerous possibilities that could span across the industry. Moreover, this offers a more efficient chiplet development and integration plan where we can develop outside of the platform an experimental test system for these targeted specialized chiplets, a targeted accelerator, test it out in the open in the laboratory side, but then work together with an integrator such as AMD, Samsung, or ARM in order to then drop it into a real professionally curated platform that they offer that enables commercial product integration of these very important and powerful specializations. So the take-home points, interchiplet protocol is good, but it's not enough. We have to put more effort into the form factor, power delivery, mechanical bump pitch, and assembly that multiple OSATs can offer services for, not just one. And for HPC, the dominant cost is the platform. It's not the chiplets, the chips, or the package. The platform is everything else in there, the firmware, the software ecosystem, the system integrators. Chiplets are a less disruptive way for us to insert those specializations into the platform. So we believe that it's very important for our future in HPC, but also for AI. And we need to have some platform-specific guardrails, for example, memory consistency models, security, and integration into a programming environment. Smaller players like startups need access to this recipe that shows how we can do this end-to-end, even if it's only preliminary, and have points of contact within our suppliers and OSATs for all steps in that supply chain. There's a new work stream in the ODSA for HPC and AI modularity, and you're welcome to join. It just started up last week. So we're having discussions about what the requirements are and what the opportunities are. And that's it. Any questions?
Yes, we do have a few minutes for question here. I think I thank John for super speed, right? To help us to buy sometimes. Yeah, anyone has a question, I think I for John or any speaker earlier, we feel free to ask. Before I think we do have a few minutes before we can start the next speaker. Yes, Shannon, I think the recorded version will be available online. So I think Kevin will be posting that. So I saw a couple of questions that asked earlier related to this.
Hi, this is Arvin. May I ask one question?
Sure.
You mentioned the platform as really being the major expense. Do you have any thoughts on how to really facilitate that or make that something that would be easier? Because you are assembling a lot of different things that are similar in some ways. Is there any way to really leverage that and create a streamlined way to do this?
So, we have discussions with existing platforms that have adopted the chiplets, and I can't detail the conversation. I can say that, for example, we've had conversations for a number of years with ARM that said, no, we're not going to do chiplets. No, we're not going to do chiplets. Now their entire portfolio is offered in chiplet form. And so that means we're in active discussions with them about then how could we leverage that? What are some crucial starting points using the IP that they already have where we can plug our stuff in? I believe that the big sticking point is, of course, we need to narrow down things like the mechanicals, the power delivery, things like that, so that ARM makes one set of chiplets instead of a different set of chiplets for each integrator. That's where they're at right now. That's not sustainable. So that's why I believe this discussion today is important, and also the discussion in the new work stream for HPC modularity is important, because ARM's made a valiant effort and they can't go further with it until we narrow down the options.
Okay, thank you.
Yep. And there are other suppliers that have chiplets platforms. We can certainly work to integrate with their platforms, and that I can talk less about, but that would essentially be adopting what their engineering practices become. So you end up connected to only a single vendor. But that would at least get this launched off of the ground. Even if we had a single vendor solution, we get a start, and eventually things will trickle out into standard practice across other assembly houses and OSATs. Any other questions?
Hey, this is Anshu Bahadur. I actually had a question, more of a comment for Arvind. Arvind, I was also interested in the quote unquote dating and marrying protocol that you had mentioned. If it's okay, I would like to kind of reach out and touch bases.
Yeah, of course. I apologize. I guess I didn't put my contact information, but I think we can get that.
Sure. Thank you.
Any other question from anyone? If not, great. I think I feel free again, like to drop your questions in the chat box. We will happy to correct them and answer them right in the follow-ups, which we're going to post right on the OCP website. Thank you again. I think for John, right, for the great presentations for today. So we happy to move forward to the next speaker, who is Huria Naomi from the TensorFlow. Huria, are you online? I don't see Huria on my list. Like, Huria, if you're online. Yeah, I don't see Huria on the list here.
I can go next, James. If
Yeah, actually we have right Narasimha next. So Narasimha, are you there? Like we
yes. Can you hear me, James? I'm here.
Yes, Narasimha is from NVIDIA. He's next after the Huria. So like since Narasimha is ready, I think we can go and start with that, and then we'll continue to see if Huria will be joining in a moment. Thank you. Please go ahead and share screen and start.
Sounds good. Thanks a lot, James. My name is Narasimha Lanka. I work at NVIDIA. We also have Ishchada from NVIDIA. We work predominantly on die-to-die IOs within NVIDIA. A lot of previous speakers have, we'll try to bring in a FI designer's perspective for 3D integration, as all the previous presenters have described the need 2.5D and 3D integration. We believe that this is the path forward for more scaling. And in general, the idea for interoperability would be data rate, and as the previous speaker John emphasized, physical interconnect definitions will be critical for 3D integration. I'll make a case for at least I'll try to make a case for the fact that with 3D integration, the solution space increases quite a bit, and there is possibility for more diversity in all the physical interconnect related stuff within the 3D integration. So this is one step deeper, from the packaging level that some of the previous speakers have talked about. This is one level deeper into die-to-die interconnect itself. And so we'll mainly focus on TSV-based 3D stacking. This is the one that is getting a lot of traction in the industry right now. Most of the industry products are predominantly based on these, or whatever is available right now. Most of them are predominantly based on, as far as my understanding goes, most of them are predominantly based on TSV-based stacking. So there are multiple flavors within TSV-based 3D stacking. There are microbump based, which are slightly larger pitch. I think I've seen a literature as low as 20 micron interface. Whenever I say die-to-die interface, this is the interface between die 1 on the top and die 2 at the bottom. What is the interface what is the interface that they are interacting with? At least the physical interface for in this particular slide, and how they are talking to each other, whether they are face to face, where the active silicon area is facing the active silicon area, or face to back, which is the active silicon area on one die is facing the substrate of the other die. So from a 10,000 foot level, all of this seems pretty similar, but once you dig deeper, there are slight differences, and which will lead to a larger array of possibilities in terms of bump pitches and some of the constraints that IC designers face today. The one on the right half, the copper to copper hybrid bonding, is, I think, the next thing that is the next focus for the industry right now, because that gives you a lot more density in terms of bump pitches, and we are going pretty much below 10 microns, and I've seen claims that they can go down all the way to 1 micron pitch. So even within each half of this, there is a wide array of physical interconnects that are possible. And within each, there is a slight difference between what the signal path is and power delivery path is. So power delivery constraints are slightly different from for each of these. So long story short, there will be a wide array of possibilities even within quote unquote 3D stacking technology at the IC and physical interface definition level. What we are looking at is there is an increased constraint based on increased constraint list based on process technology itself. So the bond pad, I'm using bond pad and bump interchangeably right now, just to avoid confusion. So essentially, micro bump and bond pad I'm using interchangeably at this point, but they are slightly different. So essentially, what we are looking at is each technology is driving a specific set of mechanisms to integrate and achieve this 3D integration, and they are slightly different in terms of rules, and that kind of limits the available bump pitch, ESD requirements, TSV keep out zones. Some older technologies might only support larger bump pitches. All of this is driving a lot of difference between the bump pitches that are being implemented right now. So especially for heterogeneous integration and interoperability, there is a need to coalesce around certain bump pitches, I think we believe that we'll start with larger bump pitches, bump pitches, even within copper to copper hybrid bonding, we'll probably lean towards the higher bump pitches at this point, and probably look at lower bump pitches at a later time. But that being said, there will be in-house specific implementations that are very custom that will go to lower bump pitches. But as the current focus is about interoperability right now, there might be need to coalesce around the larger bump pitches. Reliability is another thing that will drive the need for larger bump pitches, and also additional care for the aspect of redundancy. Again, there are certain applications that can get away without a lot of reliability by adding limited or specific coverage, but other reliability needs for auto may be pretty stringent. So essentially, we need to look at reliability aspects of it that might drive bump pitches to a larger value. So all these factors kind of force us to support for a wide range of bump pitches. That will bring us to the next item, which is the interface speeds. The natural tendency is to do whatever clock rate that we have. Natural tendency is to drive at that data rates. But at this point, we are seeing that there is more interest in logic chiplets being stacked on top of each other. And that will drive a need for larger bandwidth and throughput between these two dies. And so interface speeds might need to go up because the bandwidth per area requirement will keep going up as we stay at a higher bump pitch, but the need for throughput will continue to increase. So these are some of the opens and challenges, especially moving from a 2.5D to 3D kind of integration, where 2.5D, there is a wiggle room between die 1 and die 2, which are placed on an interposer or a substrate. There is wiggle room on bump arrangement because you can fan in, fan out. There is wiggle room in power delivery, where one side can choose to have a higher number of power bumps than the other. The 3D interconnect, as far as I can see, has to have very, very specific definition of bump arrangements, because one is sitting on top of the other, and there is no wiggle room to fan in, fan out. As far as I know, there is a direct connection between the two dies. So coalition around bump pitches, coalition around bump arrangement, and understanding of repairability requirements, which are application based. There is a need to carefully look at, do we still stay with 2.5D like repair schemes to kind of support more repair options? When do you do the repair? So there needs to be a conscious effort to keep these interfaces very, very simple. So simple and lightweight. And so all of these need to be considered when we are kind of talking about interoperable 3D chiplets. And like we mentioned before, there might be a coalition around. There might be a need to stay with larger bump pitches, even with copper-to-copper hybrid bonding. This will require per bump data rate to go quite substantially up. Like other speakers have mentioned, thermal and power delivery modeling will become very critical in this aspect, because as power density increases, hotspot might increase. So we need to find where the breakpoint is in terms of data rate, with a conscious effort on power and thermal modeling related items. That's a quick thoughts that we have. Ish, if you have anything to add, please let me know. If not, that was the extent of the discussion that we wanted to have today, James.
Yes. Thank you, Nasser Shimha. And we do have a few minutes, like opening. I think I open to questions for anyone right to ask. Feel free. I think to raise your question here.
Yeah, hi, this is Tony from Siemens. Narashima, when we get to these very fine pitch, hybrid bonding type of wafers, do you guys typically do wafer sort at that level? And if so, how do you do that?
That's an interesting question, Tony. Basically, the features need to be in there. Right now, the interest is to do the wafer sort. So again, FIs have to be conscious about being able to do that, and we are looking at features that kind of need to be incorporated to be able to do that.
So you're doing like sacrificial pads, or you're looking at other techniques?
I think we can kind of talk about these offline, but essentially there have to be features that need to.
Yeah, that is a topic that we're looking into.
Correct.
CDX, so I'd like to talk to you about that offline.
Definitely.
Yeah. Anyone else have any questions?
Thanks a lot, James.
Yes, thank you, Nashima. So I hear Sharp it's ready. I think so I think we can go ahead and move forward to the next presenter, Sharp Adharan from Innosemi. So Sharp, please feel free to share and go ahead.
Hi, James. Hi, everyone. Let me share my screen. Do you see my screen?
Yes.
Okay. Hi, everyone. Thanks for JEDEC and OCP for organizing this event. My presentation is about Innosemi company. We are doing chiplet-based silicon photonics. Before jumping to that, I apologize, James. I want to basically do a 10-second advertisement. As part of the activity of Open Compute Project, we are basically preparing a white paper on a common method on different parameters that we need to measure and how we report the performance of the available electrical phi, which, as other speakers also mentioned, is one of the important factor of the chiplet community. The activity is going on. We are ready to publish the first version of the white paper, and we are meeting on every Tuesday at 9:30. Feel free to join us. It's available on OCP calendar. Okay, what's the motivation behind to have a chiplet or optical die-to-die interface, and where do we need this optical interconnect is going to happen? This is a famous chart published in ISC 2022. The x-axis is basically the link distance from 1 millimeter all the way to 100 kilometers. These are the links that usually these days we have to target for basically the long fiber one, all the way to die-to-die, basically links like HBM activities. And on the y-axis, we do see the link bandwidth, which is kind of low, and all the way again, when it gets to the HBM, it's the most right now, at least the bandwidth requirement between the GPU and memory bandwidths. The dashed line in this graph is the kind of historical crossover when we moved from electrical to optical. All the green basically area here and green dots are based on electrical connectivity, and all the blue one and yellow and red around it are basically different types of the optical communication. You see, this was traditionally was happening when we needed basically longer reach over the 100 kilometers, 10 kilometers, or over a couple of 100 meters. We always use the optical. But there is a trend that slowly we are shifting this optical needs or optical interfaces toward less than 1 millimeter or 10 centimeters. And now we are talking about optical HBM and other stuff, which is kind of enabling the next generation of the HBM needs for high bandwidth. This is pretty much all the base, by the way, solid line that you see is already deployed. The dotted line is the projection that is going to happen. And again, from right to left, when we go towards the top of this graph, you do see the terms of CPO, which is the co-packaged optics. It's a kind of chiplets that we are co-packaging optics with the existing switch or XPUs or CPU and GPUs. And for sure, when we get to the distance of 10 centimeters and 1 centimeters, we have to do that in a package. There is no way that we can have a fiber for 1 centimeters. At least this is the trend. Again, where this shift is going to happen, basically where we are bringing back optics to the package, or some people call it the co-package optics transfer. Sometimes I'm calling it shifting optical engine into the ASIC. From the top left, this is a graph, by the way, from the fiber mall. From the top, you see the historical connection of the copper cable for the back of the chassis or back of the plane. This was a switch or any kind of ASIC. We were driving a very long reach link through the copper. Then people start replacing this DAC or copper link with the conversion of the E to O at the end and attaching it to the fiber. Then they realize still there is a long, basically reach electrical needed here, or kind of C2M link, to drive this ASIC to the converter of the electrical to optical, or as we call it, optical engine. Then they realize, how about if we bring this as close as possible to ASIC, make this electrical link, which is lossy and power hungry, shorter, and leave even that part to the optics, which is less loss and hopefully less power. And eventually people are advertising right now, and people are demonstrating this, is to bring this electrical optical engine, or E2O, O2E as we stand, electrical to optic or optical to electrical, in the same package of this ASIC or switch. And if we zoom in this category, then we're gonna have actually 4 or 5 different basically implementation. I didn't include any 3D, but there are the 3D version of this one as well. But if we keep it in 2.5D or 2D architecture of the integration, we still have our ASIC with the PHY, and then we're gonna have an MCM module here. By the way, these green ones are package substrate, is no longer the PCB of the chassis. Then the PHY is gonna communicate with each other. We're gonna have a separate chip for TIA driver, which is the needed blocks for optical. And then we're gonna have our optical modulator and photodetectors and attached to the fiber optics. Then slowly people say, okay, how about if we combine PHY and TIA driver together as a single chip, reduce the number of die, and talk to the optical? Then we actually, one more step is, let's combine everything and do everything monolithically. That's another approach that people are doing. Then PHY, TIA driver, and optics in one single die. And recently people are talking about direct drive monolithic, which they assume there is no need for PHY here. These two are kind of short distance, and the channel loss is kind of low. And this PHY can actually directly drive the TIA driver, and then there is no need for a PHY or retimer here. That's basically where the shifting or co-package optics is happening these days. But why basically silicon photonics chiplet? As you saw, it's actually led us to integrate different process technology node when we go to the chiplet approach, because photonics is in different process nodes, and we need that. And we need this kind of activity for scale out, basically enabling the scale out, assuming that we have different GPUs, CPUs, or APUs or XPUs here, and we have different memories, especially for CXL these days that people are talking about, or a CXL switch. All these things can actually happen over fiber optics. And by co-package optics or CPO or optical I/O, we can bring this basically optical communication to every individual of these blocks and make the link high bandwidth density and do a kind of power reduction. That's where basically the NSMI is coming in, and we are advertising and saying that we can enable this kind of link for you guys if you are interested. There's basically any kind of ASIC here, and NSMI optical engine can get co-packaged with your circuit to enable optical PCIe or any different kind of optical protocols that you need. What we do have in NSMI is the GOST family, as we call it, GOST M112. It's a PHY, it's an optical engine. As I mentioned, it's a direct drive. Then we don't need to be dedicated to one kind of the PHY. It's a PHY agnostic. We can support any kind of data rate from a couple of gigahertz all the way to 112 gigabit per second PAM4. It's a monolithic chiplet, which means that you're dealing with only one die, all the photonics component, all the electronics component, everything is in a single die. And excluding the laser, we are burning 4.3 picojoule per bit at 112 gigabit per second PAM4. When we say it's a monolithic, I just put I know it's a very, so much abbreviation here, but these are all the blocks that are basically sitting in these two die. For the TX and RX, there is a lot of photonics things happening and electronics stuff together here. This is our basically the result as I'm showing in 112 gig PAM4 on the left side. This is our TXI and RXI diagram for PAM4. Those are our probe basically result from the lab. And also we moved one step further and we said, okay, how about if we test interoperability? And one of the customer wanted to try this thing to reduce the latency and not using PAM4, using basically NRZ. We enable 53 gigabit per second NRZ in this mode instead of 112 gig PAM4. And our chip act as a receiver, and another company actually played the transmitter of it. And there was a SerDes by OEM, and we create this link, perfectly working. By the way, all these things were based on the eval board, no co-packaging, all the RF probes and SMA connectors, but still with that kind of connection, we maintain the bit error rate of 1 to the power of -12 without any fake, because this was basically NRC. Different example of use case could just not only be on the package. Some people actually prefer to have a conventional package to package, then we have to have a different PHY here. This PHYs, as I mentioned, could be PCIe, could be 112 gig, could be bunch of wire or UCI or different approach. We are PHY agnostic. Or we can be actually a direct drive and just couple with your PHY in the separate package. This is actually getting slightly interesting these days from the industry. We used to be on the 1 and people were jumping to 3, but now they are exploring this path as an intermediate option as well. But we are seeing also people start deploying this one. And this is basically the true chiplet, as I'm calling it, because you're putting it in the package and you're reducing the power of this PHY to get the full benefit of chiplet activities. In summary, as James asked us for it, it's our product is optical engine in direct drive. We support 16 lane up to 112 gig PAM4 per lane, total 1.6 terabit per second. It's burning less than 5, as I mentioned, 4.3 picojoule per bit. Target customers are data center. Our next focus is optical PCIe CXL and data communication. Product status, we are ready to sample. We have done some demo. Our eval board is ready. If you need it, just contact me. My email is there. In terms of business issue, we are looking for electrical partners because we are not providing the PHY. We are basically converting E to O. If you do have a good PHY, just bring it to us. Another, I think, issue and possibility of the collaboration is that in terms of the ecosystem, we need to know who owns the final product, because when things like optical is going to happen, then there is a lot of things on the photonics packaging and etc. that those issues hasn't been addressed. And I would like to spend time with anyone who is interested to, as a practice, go over those and see what's the best practice to answer those needs. Thank you, James.
Thank you, Shahab. I think I forgot presentation. So I have a follow-up questions on this. Like, how you see? I think like the standard. I think like or standardization could help in the photonics. And also a company product here.
Yeah, it's a great question. I do, you know, we have a basically optical community that they are pushing this optical standard, but their main target for years was long reach basically communication, not towards basically chiplet, or they were at the higher data rate. But I'm seeing actually this standardization is happening from the different electrical side as well. Recently, PCIe start actually a work group, and they're calling it optical PCIe. Their main target is to enable PCIe over optics. And actually, from that activity right now, they are pushing that back to the OIF. At least in these two standard body can work together and enable the optical. There's great interest from the industry. Lots of, I think, very well attended event on the optical PCIe. Even I think yesterday I was saying basically more than 100 people attending in one of the calls or events. Definitely this is an interest, and mainly for long reach PCIe when it goes more than 8 to 10 meter or 5 meter and beyond, all the way to 30 meter. That's where actually optical PCIe can stand out and enables basically a scale up.
I see. Appreciate that. I think one more thing. I think on that the very early, I think you mentioned about the file. I think or the data, right? Comparisons of the performance. I think we talk on that meeting. I think that is actually, I think I'm thinking about that something could be interesting. I think that we can make some of this kind of the metrics that we talk about. I think it could be part of the standard format that we can kind of share across. I think I create some that standard format. I think I share across industry. I think in some structured formats. I think that people can easily share that information. And that potentially can be used in the tool as well, right? The EDA tools, I think to kind of do analysis and even perform some kind of testings and for other purposes. So I think that's probably something we can talk more in the meeting I think that we have on Tuesday. I think I see how that kind of fit in that together. So we the works at the CDX as well. I think that kind of put all different kind of the mechanical electrical performance properties together in standard format, and including this kind of the electrical interface performance metrics. I think that will be very interesting to see that.
Sure. Thanks. That was great feedback and comment. Thanks.
Yes. Anyone?
I have a follow-up question, Shahab. So, we are all eagerly waiting this performance metrics comparison that probably will keep us all honest. So one of the things that caught my eye is you're mentioning 5 picojoule that you can achieve, right?
Correct.
So we've been seeing numbers like 0.1 picojoule and 0.2 picojoule, and some things are just mind-boggling in terms of I don't know what's being included where. Is there somebody who's standardizing, what part of energy needs to be included in these numbers?
Not for optical at this moment. And optical domain is actually kind of messier than electrical. For the first step, if we are working on this electrical interfaces, that even in electrical interface, it was hard actually to force people how to report power. I just want to mention something, maybe, I don't know, it's funny or sad, but someone brought this to our attention, one of our members who were attending the meeting, and said, hey, if we were simply saying, okay, these are the blocks that you need to measure and report the power, the usual stuff, but we thought that, okay, we are so proactive and we are listing everything, and we say, okay, everything in this box, you need to measure the power and report it. Then someone brought this to our attention. Okay, how about the different patterns, If I basically put the low transition pattern, what's going to happen? Basically, if I just start transmitting all zeros and just single one for a while, simple thing like that. Then we move back and rephrase basically this white paper, and we force people to report power with a specific pseudo-random sequence data pattern. The game is on, and we are trying to make it more standard, but even people do different tricks to report lower numbers. And in the optic is actually even worse. Because then there is a laser power, you know, the retimer power, you know, it's because some of the stuff is out of your hand. It's hard actually to get people to follow one thing. But hopefully after this electrical, we can get to the optical as well for sure in maybe a year.
Okay, that's great. So another question. So along these lines, what is your opinion on the chiplets for electrical and optical part of these interfaces? You think there is a big commercial activity ahead of us here?
I think it's happening, you know, at least I don't want to name companies, but we are burning a lot of power right now to make this the third link that I mentioned, which is not a chiplet based, and we need a very basically not very power hungry, but it's a good enough power that we are burning to compensate the loss of this yellow line that I'm pointing out at. And when you're bringing it to the co-package, this power is gonna reduce, and that's one of the motivation. And the second motivation is in this graph that I mentioned. Assume that if you don't want to do the co-package and you bring this out, you know, the amount of bandwidth density that you're gonna get is kind of low. Right now, the bandwidth density that we need is gonna happen at the silicon interposer level. For example, look at the optical HBM. If we cannot bring the optical engine to the advanced packaging, then we are losing that bandwidth density requirement. Then for sure, there is no way that we do it off package. We have to go through this path. But when that happens, I think market and application is going to decide for it. But we are seeing that one. For example, HBM4 is a challenge, and in electrical implementation, there is a challenge to implement it, and people are exploring that to implement it in optical.
Thank you.
Yeah, thanks again, Shahab. Anyone have any other questions? I do have a question from Bilal. I think he's asking as a Q&A session. I think he's probably asking more for Tony from Siemens. I think we do have big time. We can kind of go back to this Q&A. So he asked, could you please detail the substrate and interposer ADRs in Siemens presentation, please? Tony, are you still there? Were you able to answer that?
I'm sorry, say again, James.
His question is could you please detail the substrate and interposer ADRs in Siemens presentation?
Yeah, so the idea with the interposer and the substrate, there's really two components. One is the connectivity structure. So this would be the rules for like the bumps, the micro bumps. That's one component. The other one is the assembly rules. So that would be the spacing and width and spacing of the interconnect. So those are really the 80K type rules. Now, the other thing that we're looking into is the actual detailed layout rules. So you could actually use those to define the checks for all the passive connectivity. So essentially that would be typically that information is provided by vendors with the design rule manual, a PDF file. So the idea is we'd be able to capture those, all those rules that would be appropriate, whether it be a silicon interposer or organic interposer, and you know, in a machine readable format. And then that could be used in the design process as well as creating the PDKs.
Yeah, thanks, Tony, for that. I think we record that. I think I don't speak right here, but I think I will definitely post this question and answer. Anyone else has any question for any other speaker share? This is your opportunity to ask. I think we have a great expertise from the industry, from various areas like EDAs, and feel free to ask a question here.
This is Arvind. Could I ask one question?
Yes, go ahead.
So this would really be targeted toward the EDA experts. Could I just ask in general about a strategy or methodology for power delivery for multiple chiplets on a package? And in particular, to what extent do you need specifications for each chiplet? But since each chiplet is different, how do you avoid over-provisioning in the power that's required for the composite package?
Want me to take the one, James?
Yeah, go ahead. I think this is for EDA. Tony from EDA or Neil from EDA.
Yeah, so the first thing is you need a power model for each of the chiplets, as well as a how the power is delivered to that chiplet. So you need kind of a CPM model is a type of model that can provide kind of the internal power connectivity to that chiplet. So really then the problem becomes, how do you deliver that power within the package? So that is more of a package type power integrity analysis. So you need to understand the power structures, and then that power, if it's a 2.5D, it needs to be delivered through the interposer. So you could either just do a calculation and best guess and then measure I or drop, or better yet, if you know what the power models are in machine readable format, you may be able to automate how much power and number of pins and that need to be located. So if it's more like a 2D structure, or even just going through the interposer down through the substrate, then you also have to look at if it's a stacked die, that power needs to be delivered up through the whole stack. So again, that's kind of a divide and conquer. But again, having those power models and the connectivity, it's the problem is really performed at the package planning and analysis, I or drop, as well as power integrity analysis.
Yeah, I wanted to expand a little bit on what Tony was saying. As far as power models are concerned, really, if you don't want to over provision, what you would need is a hierarchical power model that is also function dependent, so that for a given chiplet, what the different states are, what are the different modes, what the power consumption is for different modes in different areas of the die, right? Different IPs on the die. And then combining multiple chiplets, you would need to understand the overall architecture, what is working when, right? Kind of high level simulation can give you that. And then you would know each chiplet, when it's on, how much it's on, and how much it's off, right? In time dependent, how do I say that? In time, basically, look at the temporal dependency of one chiplet to another chiplet. And that way you can get an idea of the overall power. But one thing that you definitely need to consider, at bare minimum, there's two modes of operation. One is typically, right, when we ship things to customers, they are concerned with functional mode, right? How the chiplet is working, what it's doing. But really, serious attention has to be paid to test modes, right? You don't want to be testing, if not that you don't want to, but if you're testing two chiplets at the same time, they're going to be both high power. So you have to provision for these two different modes, no matter what, right? And from that power model, you basically get, from that kind of power model, you can get the current ramps, the current ramp up and down, do package level power integrity analysis, do thermal analysis as well to see any thermal coupling between hot parts of the different chiplets. My view is that chiplets today are where we were at monolithic dies probably like 20 years ago, when at that point we used to do one total power, and worst case for all the blocks. And we found out that we cannot do that, right? And we need to go and look at different blocks, different powers and different states so that we can filter out hotspots, total power, so on. So chiplets are there. We cannot use worst case power for all the chiplets to do the design, because both power delivery and thermals are just not going to work.
Yeah, thank you. That was actually the part of my question, which was how do you avoid using worst case power? And if you do, you would end up just grossly over provisioning.
Yeah. So ideally, if you do have your detailed power models that have that granularity, that can happen. So if you're doing your own design, you can actually go down and do the fine grained power analysis. But if you're looking at a standardized model for chiplet, it's really kind of expected from the chiplet provider to provide that information, whether it be in a IEEE power model or other details. So, if they just give a simple power model for the chip, off the data sheet, that's going to kind of force you to use worst case, in which case you're creating a problem. So the more information you have and the more detail, the better you can design and optimize the project.
Yeah. So next week, when it's my turn, I'm going to talk a little bit about that, how we model chiplets and power and thermal. So, as a quick plug-in for for my talk for next week, come by and see what we have.
Thank you. I'm really sorry. Could you identify yourself? It's not on my screen.
Oh, David Rashkov. Oh, I don't know why it's coming up as James Wong.
Yeah, that's what I was wondering. Thank you.
No, I'm definitely not James Wong, and I just noticed now. Okay.
Yeah, because I think you sign in using my link. I'm sorry about that. I think that could be confusing to everyone. So
okay, all right, here we go. Okay, sorry.
Thank you, David. I look forward to your talk.
Yep, this is me.
Thanks, Tommy, and David, for answering question. Anyone have any other questions? Yeah, I just want to share. I think the program. I think we quickly skimmed through earlier today, but I just want to share with everyone again the programs. I think revisit. I think today. So we have great presentation from everyone. I think from various EDS, and the companies and organizations and the standard parties. For the next week, so we same time Friday. So we will do a quick openings again, since there could be a good new audience there. And then we will move forward with the presenters from Intel, Larita. So she has been a driven one. I think I main driven. I think for the standardization in the industry. Sorry. With somebody speaking.
My bad.
Oh, okay. So yeah. So and then for I think as David mentioned, so he will be presenting again next week. So we will hear more from him. I think on the power and thermal, and David also is a colleague in the CDX, so he will probably touch base a bit more on the some of the standardization project that we have ongoing under the CDX. After we have another EDA company, Synopsys, who is our partner. Pato will be talking about the standardization perspective on from the Synopsys side, and in following that, we have Dominic Brown from ARMS. We will talk about the all this talk will related to focusing on the standardization. So we'll see the changes from different parties, how the views this standardization can help across the industry. So which will include the next presenter actually coming from another government agency, Fermi Lab, Fahim. So will she has been presenting participating in some of the OCP meetings. So she will talk about some of these challenges, especially on the from the website. And we also have the Anur Rama Muti from Microchip. So another the chips company will talk about, I think, how again the standardization will help. We also have an educational UCLA Pune Gupta. I saw him here today, so he'll be presenting next week from the academic side or perspective. So and follow up, we also have Alpha Semis, Su Hun Fun, will present, and we also have another standard body from SI2. Matt Ross will be presenting, and last but not the least, Ira. I think I will be. Many of you know here has been active participants in OCPs from Blue Cheetah. He's read the co-read the BOW. So we will be great. I think to hear from his perspective. I think how is that standardization, especially I think correlated with some of the works that have been going under the a bunch of wires. And he generally, I think I like his spirit. I think he going to, I think I gave a very great crossing presentation there. So and then we'll do some summary, I think at the end. So if we get time, we might try to kind of see what we learn from today's meetings, and then we will probably, I think follow up, I think some of the interesting, I think topics that brought up today, and trying to talk about it and address that in the next meeting. And I think I want to highlight is that we do have a slightly longer meeting next week. I probably will update the calendar invite. We're going to extend 15 minutes since we have almost speaker. We trying to accommodate. We don't want to lose any, I think, great speakers. So we extend a bit of the time. So hopefully, I think everyone, I think I appreciate just a calendar accordingly and stay until 10:45 instead of 10:30 next week to listen from this great speaker. So yeah, with that, I think that would be kind of the highlight for today. So, and this is again, this is a QR code. I think if you guys are your phone ready, I think if you haven't signed up yet, please go ahead. I think to send that, you should able, that should redirect you to the sign up page for the next meetings for the next week. And also for all the presenter speaker today, if you haven't done so, please share your slide with me or Jawad, so that we can correct them and post that on the OCP website. I think that would be great, especially I think for future references and people will research it. I think that would be very useful information, and for some of our audience, if that would not be able to participate or may not, can go and review there. We also post the video recording, so Kevin will help to post that, and we will send email to all the participants here when we have that information ready, the video recording and also the slides. So this will be for a follow-up after the next meeting next week. So with that, we only have 1 minute remaining. Anyone have any last questions?
James, one thing, part 2 is June 21st, not June 4th. Yeah.
Sorry for the typo, it's June 21st, but I believe the QR code is correct. Reading is a part 2. So yeah, thanks for pointing out that. Anyone, any other last minute questions? If not, yeah, we will end the meetings today or the workshop today. Thank you everyone for participating. We look forward to seeing you again next week.
Thank you.
Thank you.
Bye-bye.
Good session. Thank you.
Oh, thank you.